Welcome to ChemVid. Today we are talking about the difference between fluorescence and phosphorescence. So we started these notes in class, electron configuration notes. So you just need to flip over to the next page and we are down here. So previously we talked about electron configurations and how to write them with the condensed and the expanded. And now we're going to go into more depth about how electrons move and the different ways in which they move. Alright. So for fluorescence and phosphorescence, there's a difference between how electrons move. So we've learned that when an electron is in its ground state, or the state in which all the electrons are in their lowest available energy levels, for instance, 1s2, 2s2, 2p6 is neon in its ground state. Neon has 6, 8, 10 electrons. All of them are in their lowest energy levels possible, and so that's what we call the ground state, when all the electrons are in their lowest energy level possible. An excited state would be when one or more of those electrons jump up into another orbital. So neon's excited state was when we had one electron from the 2p orbital jump into the next available energy level, which was 3s. This is called the excited state because one of the electrons is not in its original place. It's not in its lowest energy level. It's in what we call an excited state, or a higher energy level. So an excited energy level or excited state is when one or more electron moves to a higher energy level than it's supposed to be. When we do electron configurations, we just work with the last electron and move it up. But in reality, a lot of electrons can move at one time. So we learned that if I hit an electron is noted by the half arrow. We learned about those in our orbital diagrams. If I hit an electron with energy, then it's going to shoot up into another energy level. Now this energy can be in the form of heat, like what we did with our flame lab, or it can be in the form of electricity, like Bohr did in his model. Electricity, yep, that's spelled right, good. Or it can be in other forms. Sometimes I can hit an electron with just higher powered light, such as violet light or UV light or something like that, and that will also excite an electron. So this energy can be in multiple forms. It doesn't have to be just heat and electricity, but those are the two common ones that we talk about. Okay. At the bottom, this state where my electron is supposed to be, that's what we call the ground state. And then where it moves up, that's what we call the excited state. And you guys know that when an electron jumps up into an excited state, he's eventually going to fall back down. And when he falls back down, he releases light energy. Okay, and that can come in different colors. For instance, our hydrogen spectrum has 4 different colors: violet, blue-green, and red. Those are the 4 visible colors that we can see when an electron jumps up from different energy levels. Okay, so this is the general gist of what happens when an electron is excited. However, there are 2 different ways an electron can return to the ground state, and that is what we call fluorescence and phosphorescence. So I'm going to use green to denote fluorescence. Okay, so fluorescence is what you usually think of and what we've drawn multiple times. It's when you have an electron, it's hit by energy, the electron goes to the excited state, falls back down, producing light. That's fluorescence. It's very quick, and it's just an electron moving. However, there is another form. Now, if we were thinking of fluorescence kind of like a firefly, think of fluorescence as a firefly. When you see a firefly, the little bum of the firefly will light up, and then it goes away very quickly. The light goes away really quickly. And then it lights up again, and then it goes away very quickly. And it lights up again, and it goes away very quickly. That firefly is undergoing chemical fluorescence, okay? And he does that because he has a special chemical in his body that will do that, all right? So that is this quick energy jump, fall back down. Quick energy jump, fall back down. And that's what you see. Phosphorescence is more like a glow stick. A glow stick works because of a chemical reaction that happens when you break the glow stick, and the chemicals are mixed, and they release light as well. However, a glow stick doesn't last a short amount of time. It actually lasts for a pretty long amount of time. It lasts for sometimes up to 24 hours. Usually when you wake up the next morning, it might be still glowing or it might be dead, but it lasts a lot longer than a firefly. And this is because the electrons move a little differently when it comes to phosphorescence. So the pattern is the same. You still have an electron, and I'm going to hit it with energy, in this case a chemical reaction. And the electron is going to jump up into an excited state. However, instead of it falling directly back down into the ground state, it falls into another energy level. Now this energy level is not the ground state, but it is a lower excited state. So it still has some energy, but it's going to fall into that state, and it's going to produce light. And then that's a little more stable, so the electron will stay there for a little bit. And then it falls back down again, back to its original ground state, and produces light again. So as you can see, with phosphorescence, more light is being produced. Glow sticks are all about this longer process, whereas a firefly is about the shorter process. Okay? So phosphorescence goes longer, fluorescence goes shorter, but it's still the same thing. One electron is jumping up, or multiple electrons are jumping up. But with phosphorescence, you have this extra energy level that it goes to. Okay? So thinking about this different type of fluorescence and phosphorescence, you might be thinking, why do scientists really even care about electrons jumping up? Sure, for Bohr it was very important. He was able to discover that we had multiple orbits and that electrons could jump up and down. That led Schrödinger to the discovery of his orbitals, and that led us to our greater understanding of atomic theory and more scientific discoveries. But why does it matter if we know the difference between phosphorescence and fluorescence? Well, it all started, actually, scientists are just really, curious in general, so they're going to study this stuff because it's really exciting to them. However, the main thing that really got people going is what we call the deep sea king jellyfish. And this little guy, he produces a fluorescent chemical reaction just like a firefly. Only he does it for longer periods of time and in greater abundance. Okay, so you might call it maybe a little bit of phosphorescence going on here. And he has this gene that allows him to light up and go dark, and light up and go dark. And scientists were like, well, that's cool. I wonder, could we get this gene into other animals? And you may think, well, that's really weird, but biologists like to do all sorts of things by mixing up DNA, genes, see what we can do, because that's how we get our medicine, right? They're constantly thinking about what can we do to manipulate our bodies so that we get better faster or live longer or whatever. So they took the lovely gene from the deep sea king jellyfish, and they were able to place it in the DNA of little fishes. So if you notice, this guy is glowing. Now the cool thing about this guy is he is now so common, they have been able to get this process so done well, I guess, that you can actually buy these little fishies that glow at a store. If you go online and type in glowing goldfish, you can buy them, and they're in different colors, and they'll glow, and they're just like goldfish, so they'll die really soon, but, not any more fast, or not any quicker than a regular goldfish. But they do glow. So that's kind of interesting. And then they were like, well, what if we took it out of marine animals, like fish and jellyfish? And what if we went into rats? Because, of course, rats are, our best test subjects. And so they were able to see that if they could put this gene into rats, they could actually make rats glow. Weird? Yes. But kind of cool. So now you have glowing rats. And then they were like, okay, well, rats are a smaller creature. What if we wanted to put it into a larger creature? Say, a pig. And they were able to get the pig into this glowing gene, to accept the glowing gene. However, they noticed that only the cartilage would glow. So the pig itself wouldn't glow, but like his nails and his snout would glow. Interesting? Yes. But they didn't stop there. Then they were like, well, what if we could get it into a higher form? And so they decided to test monkeys. And they were able to put the gene into a monkey, and bam, you have a glowing monkey gene. And now I have read about them having glowing people genes. However, it's very unethical to do this to a human. And they are also, if you're glowing like this, it might make it harder for you to hide. So animals in the lab, we can protect. I mean, like, they don't have to worry about predators coming after them. But could you imagine a human being trying to, I don't know, duck and cover from a thief, and they are glowing? So, there are different applications when it comes to humans. But I have heard that they are able to do that. It's just that they don't think it would be ethical. Alright, so we have our monkeys. And I don't know how many of you guys watched Sherlock, but if you recall, they had an episode of Bluebell, the glowing bunny. We also have glowing bunnies. Okay. And then, that is all cool, and that is really awesome how they worked that out. But they were even able to discover how to pass the gene directly to their babies. So a bunny was genetically manipulated. Then she had a litter, or I don't know what a bunch of, I think it's called a fluffle. Yeah, a bunch of baby bunnies is called a fluffle. I remember that. Okay, so we have this fluffle of bunnies, and 2 of them were born with the glowing gene. So they've been making great progress at being able to manipulate genes and being able to move down this fluorescent gene. And one of the nice things about a fluorescent or a phosphorescent gene is that they are easy to spot, and it's easy to see if they did it correctly or not. So there you have it, fluorescence versus phosphorescence, and how it can help us understand gene modification. And fluorescence and phosphorescence might just be a cool thing to see, but it also helps us with our medicine and being able to help people in other areas by studying how genes work and things like that. So another reason why we care is because where our electrons dwell actually tells us a lot about whether they're conductors, semiconductors, insulators, whether they're magnetic or not magnetic, whether they're strong magnets or weak magnets. So if you look over here, we have an orbital diagram. Can anybody tell me what is the identity of this element? And the correct answer is manganese. So, as we know, metals are conductors, metalloids are semiconductors, and nonmetals are insulators. And we're going to go into why that is the case more next unit. However, for right now, I want to talk about magnetism. Okay? Magnetism occurs when electrons are positioned so that their electron spin is going one way, giving them a kind of like a positive charge. And then another electron could be coming around, or another element could be coming around, and this time his electrons are going the opposite way, so he has a negative charge. If you look up here, manganese has 5 electrons that are all going the same way. This gives him kind of what we call a charge, or a magnetic dipole. Alright, so manganese is going to be magnetic. Now, if I went like this, and change this instead to zinc, you can tell that I no longer have that charge. So zinc is not magnetic. So when we're talking about properties of magnetism, we can use our orbital diagrams to see, do they have any similar characteristics in the d orbital that would cause them to be magnetic. So that's it for today. Go ahead and finish up your notes, study real well, and I'll see you next time.